I'm sorry, I forgot to press the recording on because of the time. Sorry. So yeah, I'm Sanjini Mitra. I'm the host and the chair for this session on data ethics and statistical reasoning, theoretical insights, and practical applications. So again, we have 15 minutes per speaker. We have 3 speakers, and I want to go ahead and introduce the first speaker, which is Dr. Nicole Lazar, who is the professor and chair of the department head of the Department of Statistics at Pennsylvania State University. So because of time, I'll go ahead and hand it over to you, Nicole.
Okay, let me try and share my screen here. Sorry, oh, okay. Can people see my?
Yep.
Okay, I'll just make this full screen. Sorry. Okay, how's that? All right, and can you hear me okay? All right, so I do have a bit of a cold, apologize for that. I'll try to get through the talk as I can. So yeah, so my topic today is the ethical problems of a threshold. And I'm going to just give a very cursory overview, I guess, of some of the issues that arise with the use of a threshold. Uh-oh. Okay, so I'm going to start with a little bit of an analogy and a thought experiment. So I'd like you to imagine that you're a student in an introductory statistics course. And according to the syllabus, if you want to have a grade of A at the end of the semester, you need to have an average score in the course of at least 93. So that's taken over exams, quizzes, homework, labs, etc. All of the work in the course, you need to have a grade cumulative average score of at least 93 to get an A. So a score greater than or equal to 93 gets you an A in the course. Unfortunately, at the end of the semester, your average score is 92.8, which is less than 93. So we've all been students. Some of us are faculty as well. So we've probably encountered situations like this one. And so what do you do? What might a student do in a situation like that? So this is the thought experiment and the analogy. Here's a different scenario, or I would posit that maybe it's not that different of a scenario. You are a young faculty member and you're doing the data analysis for a paper describing your research of the last 2 years. And this is a really important paper for you. The results are key, maybe for an upcoming grant proposal that you're getting ready to submit, or maybe for just getting those results out there published. And so it's really important. You're looking at a promotion, and so you need to get that result out there. Now, you're planning to submit to a particular journal that has a policy that may be written, may be unwritten, but even if it's unwritten, everybody sort of knows that this is the game, that they will only publish so-called statistically significant results. And those are defined, again, whether formally as part of the journal's editorial process or informally through the grapevine that everybody knows that this is what you need to have. Statistically significant results defined, let's say, as those with p-values less than 0.05. So if your p-value for your analysis is less than 0.05, your paper might get accepted and you might get your grant funded and you might then get your promotion. You do the data analysis for your main results and you get a p-value of 0.053, which is greater than 0.05. So what do you do? And this brings us to the ethical problem of a threshold. So in both situations, there's an arbitrary threshold. Now, sometimes you need to have a threshold. So when you're setting grades, for instance, it's an unfortunate fact of life, but kind of necessary. In most courses, again, my thought experiment was on an intro stat class. Everybody can't get an A. So you need to have some way of deciding these are the students that are going to get an A, these are the students that are going to get a B. So it's an unfortunate but necessary fact of life. But whether it's necessary or not, I would claim that that same ethical issue arises. And that is, do I, the individual, in this case of the introstat student, the student, in the case of the researcher, do I try to game the system in some way? So again, we've all been students. Many of us are also faculty. What do you do in a situation like that as a student? Well, you go to the professor. Can I get some extra credit? Could you regrade that assignment? I really need the A, right? So people, we all have strategies, right? For trying to get to the point that we need to be for what we think that we need to achieve. What about for the researcher? So I can't, as a researcher, I'm not going to go to a journal and say, please accept my paper, right? There's a different issue there, but I would claim that there's still an ethical problem that arises. And so I want to talk you through sort of various scenarios of what a researcher might do in the situation that I described. So I'm calling this, for lack of a better term, a trilemma. Instead of a dilemma, we have a trilemma because I claim that there are three sort of typical paths that people will take. And I would want to emphasize here, there are a lot of subtleties that I'm just eliding because of lack of time. But if you look at the work of Fisher and of Neyman and Pearson regarding inference and how to do hypothesis testing, there's actually a lot of subtleties there that kind of get ignored also in just our day-to-day work. And so I'm just putting that out there, but I'm not going to go into it any further unless there are questions, if we have time for questions. So this trilemma comes about because, again, there's sort of three typical ways that people will go. So one option is to treat values that are above and below the threshold very, very differently. Okay, so this leads to statements like, there's no difference among the groups, p greater than 0.05. So even if your p-value was, let's say, 0.052, so kind of close to 0.05, what you would see in a paper would be something like, there's no difference among the groups. This also is things like statements like, we accept the null hypothesis, right? Which essentially implies that there's no difference among the groups, but that's not a statistically valid statement. It also leads to statements like, the groups are meaningfully and statistically significantly different, p less than 0.05, even for p-value that's, again, very close to 0.05, but on the other side of the boundary. This also is, in a way, sort of meaningless in the sense that you could have something that has a small p-value, but still not be meaningful scientifically. And so we'll often talk about sort of scientific versus statistical significance or practical versus statistical significance. So this is one thing you could do. You could just treat those outcomes as very, very different just based on the threshold. Another thing that you could do, and I sort of like this XKCD cartoon because it sort of shows a lot of what goes on in real life. Okay, so we've got this area here, which I'm going to ignore for now. I want to focus on these values here that are sort of close to 0.05, which is your sort of typical threshold, and the responses. And here we see things like, oh, this is on the edge of significance. Oh, this is highly suggestive. Oh, this is significant at a different level, okay? So the second thing that people will sometimes do is to use these, what might be called weasel words, but that's maybe a bit harsh. They use terms that, again, have no statistical validity, but try to edge towards this notion that, well, we're close to having something that is statistically significant. So a trend towards significance, on the edge of significance, in the direction of significance, highly suggestive of significance, and so on and so forth. But again, statistically, these have no meaning whatsoever. So this is another thing that people will sometimes do. The third thing that people will sometimes do, and this is really the crux of the ethical issue, is that they will massage the data until they get the result that they want. They will massage the data until they confess. So some examples here include something that's called hypothesizing after the results are known, wherein you look at the results and then you build your hypotheses rather than the other way around. You should obviously build your hypotheses and then use the data to test those hypotheses. P-hacking, which involves trying all sorts of different analyses and then reporting the ones that give you the quote unquote statistically significant results. And then sort of more serious are a group of practices that are called questionable research practices, or QRPs, which are things like changing your endpoint of your analysis, looking at your data at a midpoint, and without doing anything like sequential analysis to correct for that, changing your sample size, and various other practices that people will sometimes engage in. And so this is a third thing that people could do. Okay, so you can either treat the values on one side of the boundary very differently from the ones on the other. You can try to kind of say, well, we're kind of close, or you can engage in this data massaging And again, there's a lot more here, but in the interest of time, I'm only briefly mentioning what the various options are. So is there another way? Well, I would claim that yes. So first of all, there's many proposals already out there in the literature for alternative approaches. But I would claim that best practices should involve adherence to some strong principles. And I would also want to emphasize here that this is not a knock against p-values in and of themselves. Any measure that can be thresholded, which is most statistical measures, are going to encounter this same type of situation. So with Bayes factors, there's thresholds out there for Bayes factors. Effect sizes, there are thresholds that have been published for effect sizes as well. So this is an issue that arises in many areas of statistics. And so whether you're using p-values, Bayes factors, effect sizes, or any other statistical measure, what I would urge is to think about these principles, which the first four of them are called ATOM, A-T-O-M. So first of all, to accept uncertainty. So the p-value, Bayes factor, effect size, those themselves are random variables. They're functions of the data, and hence they're subject to noise. So we need to accept that and not treat them as if they are set values that are known and clear and without any variability to them or any noise in them. That's one guiding principle. The next three are sort of bundled together, and that is to be thoughtful, open, and modest. What I mean by that is you should report what you've done. Give me more information, not less. So if you just tell me that p-value, you ran a t-test, p-value less than 0.05, you've given me very little information. Give me the p-value itself. Give me the means of the groups. Give me the standard deviations of the groups. Give me the information that I need to really understand the full picture. Recognize also that one study does not present a complete picture. And again, that's sort of obvious at some level, but people will often forget it. Coming along with this, we want to avoid exaggerated claims in either direction about the importance of an effect or the lack of importance of an effect. So this is the modesty piece. And we want to focus on substantive implications of estimates and intervals. So again, not just looking at the p-value, is it less than 0.05? The confidence interval, does it include 0? But really thinking deeply and carefully and in a nuanced way about the implications of the statistics that we're calculating and using them in an appropriate way. And then sort of the harder thing, but probably the most important in some way, is institutional change, I see. So we can go from atom to atomic by instituting change at the level of the journals and the funding agencies as well, so that this different type of approach where we're trying to get away from what is essentially an arbitrary threshold that has just become convention over the years into a more nuanced and deep way of thinking about our statistical results. And that's going to require change. For as long as journals adhere to this notion of only publishing statistically significant, quote unquote, results, then that's what researchers are going to do. And then we're going to still end up in this dilemma or trilemma of having the threshold that we then need to work around. So this was just a very high level introduction to some of my thoughts on this topic. There are obviously a lot of details that I've glossed over in the interest of time, but I will just stop here. And if there's, I don't know if there's time for questions, or if there are any questions, I'd be happy to take them.
Thank you, Nicole. That was great. I think we have to probably move on in the interest of time, but if there are any questions, please feel free to share on chat. So I will now like to introduce our next speaker, Dr. Jinbo Chen, who is a professor of biostatistics and director of the Statistical Center for Translational Research in Medicine in the Department of Biostatistics, Epidemiology, and Informatics at the University of Pennsylvania Perelman School of Medicine. So over to you, Jimbo.
Thank you, Sydney, for organizing this wonderful session. Let me share my screen. Share. So let me just 1 sec. So this is a view. This is a full screen. Okay. So I'll actually just talk about a piece of work that I have been collaborating with my former advisee, Dr. Le Wang from the Department of Mathematics, Statistics, and Data Science currently at Loyola Marymount University. So so I will talk about a motivation example. Then I will go through the constraint maximum likelihood approach we developed for our problem, and then a improvement of the problem through a propensity score matching approach. So I will talk the details about this now. Okay, so first, just as a motivating example, so electronic health record data have been in recent years have been used intensively for developing risk prediction models to empower healthcare providers for identifying high-risk patients, for supporting timely personalized interventions, and better resource allocation. But there is a limitation for EHR data. EHR data are primarily collected for clinical rather than for research purposes. So it does not, often it lacks crucial predictors for accurate risk prediction. So to really improve this limitation, a solution is to collect necessary useful predictor information from external resources. And then in the end, to actually justify this extra effort, we want to evaluate the added value of the external risk predictors. And then the value of external risk predictors is assessed through comparing the predictive accuracy of the model with or without including the external risk predictors. So here is just a slightly more concrete example. So for assessing the risk of breast cancer, the current standard model is called the GALE model. It's the breast cancer risk assessment tool developed by the NCI. So it predicts the absolute risk of breast cancer for women. So it's the probability that a woman would develop breast cancer during a given age period. So this model was developed by Dr. Mitch Gill in 1989. So after that, so a series of studies has validated the performance of this model. So we wanted to actually evaluate the added value of mammographic density measured as a percentage mammographic density, percentage of dense area on the mammogram image, or other density measures from the alternative imaging modes. So then the source data we have access to for mammograph data is from the Penn Medicine Biobank. So then we want to actually incorporate the density data into the GALE model to see whether it leads to improvement. But the challenge of using the Penn Medicine Biobank data is that the Penn Medicine Biobank is actually a heavily biased data source. So it's nested within the Penn EHR system, and then patients actually were voluntarily recruited into this biobank. So biobank patients actually are systematically different from Penn Medicine patients, and the Penn Medicine patients, of course, are different from the general population. So then so just as a summary, to use the Penn Medicine Biobank data as a data source for evaluating the added value of mammographic density for predicting risk of breast cancer, there are multiple levels of challenges. So then the Penn Medicine Biobank data is richer than any external data source we have access to, and then the distribution of predictors is different, and it's very possible that the relationship between breast cancer and the predictors is also different from the general population. For example, if the general population is a Caucasian woman population, then the association between the breast cancer and breast cancer risk and the predictors in the biobank may be systematically different. So if we ignore these multi-levels of difference, then the risk prediction model we are going to develop solely out of parametric biobank data may not be useful. And the further challenge is that, let's say, even if we actually just fit the model, we want to evaluate its usefulness, we don't have any external data source that have a representative data source that have all the data available. Okay. So then to overcome this challenge, we develop a constrained maximum likelihood approach. So this method was published in Lifetime Data Analysis Journal in 2024, led by one of the former advisees. So our goal was that we wanted to develop a risk prediction model that incorporates both standard and new predictors. So in the end, because we did not have a did not have a representative data set from a target population for validation. So we prioritize the desire of getting a well-calibrated model. We wanted the development model to have a good calibration in the target population of interest. So then because we don't have access to an independent validation data set, so this ensuring the good calibration by this method actually would bypass the requirement for independent validation sample from the target population. So here, just a quick overview. So individual level data includes binary outcome, yes or no, case control status. So just for breast cancer, it's breast cancer status within 5 years of a negative mammogram screening, for example. So X includes standard risk predictors. So it includes age and reproductive factors, family history, and the Z is new risk predictors. So in this case, it's a mammography density. So we have ID data. That's a biased sample from the population. So our solution actually does require something extra. We require summary level information from the target population. So for breast cancer, so we have access to a well-calibrated risk prediction model, i.e. the Gale model. And also we assume that we have access to representative data set from target population that only has data for standard predictors. For example, the National Health Interview Survey includes the data from all the standard risk predictors for breast cancer. So our method actually allows the regression coefficients, the association between outcome and the predictor to differ between the source data and the target population. And so we also allow the distribution of standard predictors to differ between the target and the source population. But there is a price to pay. We assume that the conditional distribution of the new predictors that's only available in the source data, conditional on the standard predictors. So the probability of Z given X is the same between the target and the source population. And we enforce a parametric relationship between these two sets of predictors. So that's here FZ given X. So our interest is to for this constrained maximum likelihood approach, our interest is to fit a working model, working parametric model for this outcome Y given both standard and the new predicted XZ to fit this parametric model G beta XZ. So then the goal is to estimate this regression coefficient Z. So in the end, we use this model G for the prediction. So how do we form the constraint? So just to make the story short, so our idea actually aligns with the Hosmer-Lemma show goodness fit test. So we assume, okay, let's say we have access to the standard risk prediction model, Gale model for breast cancer. So then we divide the risk the predicted risk by the standard model into I risk intervals, which we refer to this AR and BR. So because this model, we assume it has been widely validated. So we assume we have access to the average risk within each risk interval in the target population. So to fit our new model, expanded model, G, that's our working model of interest. So we require that. So the average risk within the same risk interval by this new model would be very close to the average risk by the standard model that only relies on the standard risk predictors. So how close they are, that's actually the tuning parameter we would enforce ourselves. So then we just maximize the standard likelihood function in the source data under this constraint. So by enforcing this constraint, we actually ensured the calibration of the developed model in this target population. So here just a short figure in the manuscript showing that. So the expected rates under the expected event rate by the standard model and the expected rate under the new model, they are very close, showing that our method worked well. So a limitation of this approach is that the approach only enforced the calibration, but we all know that in the prediction setting, good calibration does not necessarily guarantee the good accuracy as quantified by the area adequacy, AUC curve, predicted value, and so on with the standard risk predictors. So there is a seminal work by McIntosh Pepe saying that really the predictive accuracy, the best possible predictive accuracy measured by AUC is achieved when the working model actually characterizes a true underlying relationship between response variable and all the predictors. So because of this, we want to actually get a model that's as closely as possible to the true relationship. Okay, so then for this, we actually propose a propensity score approach for matching. So our question is that, is it possible to select a subset from the source data that resembles the target population in terms of a joint distribution of all the predictors? So then we actually just apply the standard propensity score matching learned from the causal inference. So propensity score in the causal inference setting is to match the treated versus the untreated patients to reduce selection bias. So our approach actually follows closely from their approach, but for a different purpose. So because of time, I won't actually go through the standard steps of this matching process, but then I just want to show you a quick result. So in the end, I just want to show you two columns. So if we did not do the matching, so if you look at the naive MLE that just fit the standard maximum likelihood approach to the source data, we see a lot of bias looking at the red column. And by our approach, our approach is nearly unbiased through this constraint method and combine the constraint MLE method and the propensity score matching. So I'll just conclude saying that our constraint maximum likelihood approach and this propensity score matching together help us achieve both calibration and high predicted accuracy when we have a biased data source, but we have access to some skeleton information from the target population. So thank you.
Thank you so much, Jimbo. You can actually look at the chat, and maybe if anybody has questions, you can put it in the chat, because I'm just going to move on to the next speaker, which is actually me. So thank you very much, both Nicole and Jimbo, I will just share my screen and get started, but please feel free to stay or, and then again, see if there are any questions in the chat. So let me share my screen. Give me 1 second. All right. Sorry about that. I'm just going to put it in full screen. All right. Yeah. Hopefully you can see my screen. So I'm just going to get started. So I'm Sanjini Mitra. I'm a professor in the College of Business and Economics, particularly in the ISDS department, which is Information Systems and Decision Sciences at California State University in Fullerton. So today I'm going to talk about some ethical aspects in analyzing health and fitness tracker usage data among college students. So this is a joint work with a student of mine, and it's I don't go into a lot of depth in terms of the statistical analysis. It's mainly like an exploratory study. So and then kind of looking at the data, understanding the data, and just pointing out some interesting patterns. So to start, I'll just give a little background. Again, I'm just going to keep it short, and I know this slide probably looks a little wordy. So electronic fitness trackers, as you know, they become very popular, especially with the young generation, even I guess people of all ages, since especially after the pandemic, this became very popular for people to keep track of their health and fitness levels. And fitness trackers not only aid in monitoring physical health, but they also play a role in stress management, mental well-being, and they are all crucial aspects of life and also college life, because this study particularly is on college students. So they can, help students identify areas of improvement, make informed decisions about their health, ultimately supporting their academic and personal success. And HHS recommends at least 30 minutes of daily physical activity. And just a quick overview of some of the literature, again, keeping it very brief. So to date, fitness trackers are not well understood, and research studies about the impact of these devices have reported kind of mixed, findings, especially at the beginning, because at that time we didn't have very sophisticated trackers, but of course, over time, these have evolved, and, they can track a lot of, statistics, like health statistics, not just, tracking your number of steps and active minutes, but they do a lot more than that. There are some studies, there's one here that found wearing fitness trackers increased users' level of physical activity, like daily step count, and physical health, like blood pressure, resting heart rate, body composition. There are some other studies that did not find any effect of fitness trackers on subjects' overall health, or weight loss or fitness. And it is in some cases, financial incentives are also provided, but sometimes they help, sometimes they don't. And then there are a lot of company-based programs as well. A lot of organizations and companies have started also providing these trackers to their employees to kind of promote their healthier lifestyles and for their overall, well-being. Some ethical issues, and these are again kind of general and probably relate to a lot of health related studies, which involve data related to people's personal health. And there's these ethical issues underlie collection, analysis, reporting of data related to an individual's health and fitness. So there are privacy concerns, and again, I'm just going to go through them, quickly. Privacy concerns, of course, how health and fitness data are collected, stored, and shared raises privacy concerns, and users must be informed about what data are gathered and how they will be used. And obviously, consent is an important thing. Ensuring that individuals provide informed consent for the data to be used is crucial. It's crucial, for transparency in data usage and policies are also essential to maintain trust. and data security, of course, like after you collect the data, protecting the data that you already collected, all this sensitive health-related information, in order, it's very important in order to prevent unauthorized access and breaches, that's very vital. And robust security measures are therefore very necessary in these cases to help safeguard data integrity and maintain the security and of the data. And there are some potential misuse situations that happen. So obviously there's one thing that there's a new that I heard very recently. It's called the function creep. I know what it means, but that whole terminology was kind of new for me. I heard it a few months ago. So it's basically the risk that the data is collected from one purpose. So we all go through IRBs and all of that to before we to get the permission to do these surveys, collect this data from students or any individuals, but in my particular case, from students. But obviously, sometimes there is a risk that the data that are used for a certain purpose, as it's stated in the IRB, may be reused for something else. So, and without, obtaining explicit consent. So that pretty much constitutes a case of, misuse. And also there's commercial exploitation, like health and fitness data may be used for targeted advertising. So, you never know. So that's why, protection and all of those are important. So we want to make sure that, anybody dealing with any kind of, health data to kind of keep those in mind to kind of, avoid, the ethical concerns about exploitation and other things. So there are other ethical issues. Again, I'm going to go through this quickly. So there's, and how to address those bias and, discrimination. So we want to make sure that the data sets that are collected are representative. So for example, in my university, we have a very large minority group of students. So it's a minority and Hispanic serving institution. So, but we want to also make sure that but in some other cases, it might just be the opposite. Then there are less number of underrepresented or marginalized students. So, try to keep their data sets as balanced as possible. And, and our systems also should be designed to minimize bias and fairness across, diverse population, and also having transparency, accountability for like clear data policies and implementing checks regularly to ensure that ethical data practices are happening. And then some best practices include inclusive data collection, like I said, just mentioned, to make sure that they're representative of all demographics, to avoid bias and discrimination, and developing guidelines and standards for ethical data analysis to protect user rights and promote responsible use and reporting. So again, I'm just going to go through the things quickly. So there's a brief overview of literature review of some of the ethical issues. So they have been studied in the literature, obviously. And there have been all of these literature. So all of the issues that I mentioned about the privacy concerns, informed consent, misuse, biases, transparency, ethical framework. So these are all the, resources to, that actually address some of these issues and, discuss some of these situations. I'm going to now briefly describe the study that I did. Again, kind of an empirical, exploratory study. So it's trying to identify how fitness trackers impact personal health and wellness of college students and the underlying ethical issues. So basically identify how fitness trackers impact personal health and fitness. And although many people buy into the fad of owning such a device, I guess this was probably more a few years back. I guess now it's become more mainstream. And obviously the question remains as to whether or not these devices truly help people achieve a healthier lifestyle. Investigate differences in tracker usage for different subgroups of the student population as defined by background health, behavioral, and demographic factors, and how do factors related to privacy, security, usability, and acceptance affect fitness tracker usage among college students? Do they pose obstacles to more widespread adoption and any changes after the pandemic? So, so we just kind of look at a few different aspects. And just to go over the data, and again, I know there's not much time left, so I'll just go very quickly. So the data were collected using an online survey administered to a collegiate subpopulation enrolled in a 4-year public university. Obviously, we went through all the IRB, approvals and all of that to make sure that we, kind of abided by all the policies and all the requirements. It was was a cross-sectional study. We did not provide any incentives, again, not to kind of bias the data collections. I know a lot of students, with the incentives, they can just answer the questions really quickly without paying too much attention. So again, trying to minimize, those kind of issues in data collection. We had a relatively small sample size. We had about, it was also done on a small group of students. We obtained about 95 students who responded, about 87 valid responses. And we used statistical tests and models to analyze the data and, find in kind of gain some insights into what was happening. And we calculated effect sizes and all of that. Although we had a smaller sample size, but we made sure that the statistical analysis was valid and rigorous, so that the results, the conclusions were meaningful. So all these variables in the study, as I mentioned, we collected very detailed background information from the participants, so demographic background variables, health background, their health goals, technology efficacy, and social networking usage, and then also apart from the background, obviously, then we looked at how students, their usage patterns and what they were tracking, how they were using it, and also how frequently they were using social networking features to connect with friends and all, who were all kind of there are competitions and things that go on with respect to how many steps they're achieving every day and things like that. So, and also self-perception of impact of health and the motivation to stay healthy. And we also collected data on privacy concerns and also hindrances to usage of fitness trackers. So there were, so if they're like, what are the potential the factors that can cause hindrance to adoption of these health and fitness devices? So again, there's a background, and I don't want to go through all these details. So as I said, we have a minority serving institution and Hispanic serving institution. So we do get a lot of students from underrepresented groups, but we do kind of want to do that. So I make sure we collected that information. So we look at differences, among between the different groups. So all of these, so health background, health goals, and also technology and social networking background, because how you need to sync your device with the with your phone and then track those, all of those things, like in the beginning, like we did a similar study a few years back when the Fitbit was very new, and at that time a lot of students were not even familiar with those things. So it took a while for students to get used to it. But of course, now there are more sophisticated devices and everything. So I'm just going to skip through. And these are some of the main reasons of fitness tracker usage. So obviously to improve health, stay healthy, to become or stay physically active, monitor your health, to track your diet and sleep patterns, or to compete with friends, family, and colleagues. And then some of the results that we found, there were some students, obviously we found that female students are more likely to use them. There was some association of tracker usage with race and ethnicity. Also, people who had health goals and who were more conscious about maintaining a healthy lifestyle were more likely to use them. And some of them are not surprising findings, but it was good that our data kind of supported some of the things that we kind of thought. And then also students more familiar with technology or mobile apps were more likely to use them. And factors, actually, when we did some of the statistical tests and all of that, we found that gender, ethnicity, education level, employment status, exercise levels, pursuing health goals, technology usage, those are some of the factors that had a positive association with increase with tracker usage. And some factors that did not impact tracker activity was age, marital status, overall health condition. I mean, there are some aspects of health, exercise levels and things which were associated, but not generally. Like if you ask them about their overall health condition, BMI, presence of a chronic condition, and things like that. And and then I'm just going to skip over. I know this time is limited. And then this is some of the impacts. So most impact was felt for individuals who are more aware of their well-being and effectiveness. And the least impact was realized in the area of work. So they didn't feel like kind of overall that it was not impacting their performance at work. Because a lot of our students, especially in the College of Business, they work either part-time or full-time. So we kind of had that, variable in the study as well. Privacy concerns, and a lot of the students we found were very unclear about all these issues, the privacy security issues related to data usage, the confidentiality of the health data that was being collected. But But some of them also did think, almost nearly 50% thought that these concerns hinder tracker adoption also, because they're concerned about how this data will be used and where it will be shared, and so on and so forth. But anyway, I'm just going to skip over, and they did some prediction modeling, and some of the factors I said, came out to be significant, but obviously not all of them, when you control for the others. And then some conclusions is, obviously this was just an initial study. We are in the process of collecting data over time to increase our sample size so that our statistical tests and analysis have more power. And also ethical considerations are maintaining the anonymity of privacy of the students is important. So you want to make sure that we protect the data with the relevant technologies, including even biometrics or even multi-factor authentication, things like that. Also, always making sure to abide by IRB protocols, and also accurate reporting and of the results, and understanding the study limitations, is also very important. So those are also there, and we are kind of working on all of that, and more in-depth research also on the ethical issues, because this has become a lot more prevalent now with AI and generative AI and things like that. So we're working on that as well. So thank you very much, and I apologize for going over time. Are there any questions? Otherwise, we can go to wrap up. But thank you so much for attending, and also thanks to the speakers as well. So I'm going to stop the recording, but I'll stay on chat. But I don't know if I need to. There might be another session coming into this Zoom room. So thank you, everyone. But I'll stay on chat for a couple of